welcome to the module. In last module we were discussing about ECG signal conditioning and signal processing using operational amplifiers. So, to continuation with our previous module. So, in last module we have also discussed about what are all the factors that influence our output ECG signal and what processing steps that we are doing in order to remove the unwanted signals those are available in the ECG. In this module we will see the other type of filtering unit which is essential in order to remove unwanted signal in that. So, last module we have seen high pass filtering, low pass filtering and what frequency to be used we discussed in the last module. In this module we will see a notch filtering which is used to remove the power line interference, and we will be using a narrow band notch filter. The reason is that we require only to remove 50 Hz signal, and anyway the odd multiples of the power line interference was removed by using low pass filtering. So, our range of the complete interest is in the range of removal of 50 Hz signal, that is due to our power line interference or the operating frequency of our systems or AC input signal. So, since we are not interested in any other frequencies, if we can design a notch filter with narrow band where the interest the removal interest is only 50 Hz, it will be really great. Even if it is not, as long as our QRS detection is able to do that, as long as if we design a filter which cannot remove the actual requirement of our input signal, our job is done. So, now we will see how do we do the notch filtering using operational amplifiers, how to verify the functionality of the system and what are all the connections that we are making it, right, and experimentally as well as simulation wise we will see the frequency response as well as in a time domain response to understand whether the notch filter is filtering at the 50 Hz frequency or not. Okay. So, similar to that of our previous filtering modules, even in this case we will be using an active filters. The reason is because of very high input impedance due to the operational amplifiers, very low output impedance, and the gain is easy to set using our operational amplifiers. Now when we look into our experiment to design and build an op amp based ECG signal acquisition, conditioning and processing of PQRS wave on compute BPM, we will see how to do the notch filtering using the operational amplifiers here. So, if you see, as we know the importance of a notch filtering in our application, if we see, and we also know how to use a passive notch filtering circuit, it is similar to that of our passive notch filter. So, we are using two different resistors which are 12 mega and 12 mega and capacitors C1 C2 which are all 270 picofarad and other resistor 6 mega and 540 picofarad. Now, what makes us to select these particular values? So, since our interest is completely on elimination of 50 Hz signal, if we can calculate our cutoff frequency, as we already know the way to calculate our cutoff frequency is 2 pi R1 C1. So, when we substitute the value of the capacitor as well as a resistor, so we get approximately of 50 Hz, and the selection of R2 and R3, R1, R2, R3 should be such a way that, so R1 and R2 should be same. I followed R1, R2 to be same as well as C1, C2 to be same. Similarly, the relation between R2 and R3 is R3 value should be double than that of our R2 value, as well as R2 value should be double than R2 and R1 values are double to that of our R3 values. So, that is the reason, since we are selecting R1 and R2 as 12 mega, so R3 should be of 6 mega, and similarly C3 value should be double than C1 and C2 values. So, we are taking C3 capacitor as somewhere around 540 picofarads, right. Now, how do we test this circuit? So, similar to that of our previous thing, we will connect our input from the signal generator, which is of an amplitude of 1 volt, and since if we observe here, op amps are just used to provide some buffering or some impedance matching. So, we are not using any kind of a gain in this case. So, when we apply input signal of 1 volt, we get an output also as 1 volt. So, when we keep on change our input signal from 1 hertz to somewhere around 100 hertz, why do we not to go with below 1 hertz and why do we not to worry about more than 100 hertz? The reason is that we have already this particular stage of filtering is comes after passing through high pass filtering and low pass filtering, and we already know that the high pass filtering, the cutoff frequency is somewhere around close to 1 hertz, and low pass filtering cutoff frequency somewhere around 100 hertz. Even though when you are looking for the frequencies lower than that as well as higher than that, which are not in our interest, we do not have to even test our circuit in that operation range. So, the complete area of interest, complete frequency of our interest is between 1 hertz to 100 hertz frequency, and this particular circuit is designed to remove the narrow band of 50 hertz. So, since 50 hertz is also between this particular frequency, the purpose and the requirement can be completely monitored using this particular range of frequency. And when we apply input, we will slowly change different frequencies from 1 hertz to 100 hertz with a factor of 10 hertz in steps, and we will see observe at what particular frequency the output amplitude is 0.707 times lower than that of the input signal. That 0.707 times is because of our minus 3 dB point. So, if we can calculate the minus 3 dB point, or if we can know at what frequency that the output is smaller than 0.707 millitimes smaller than that of the input, that particular frequency gives us the information of our cutoff frequency of our notch filter, right. Why this is called notch filter? The reason, as we know that when we see the frequencies, this is how the representation of our notch filter. These particular frequencies will be completely allowed, as we already seen in our other modules, and this particular frequencies is also completely allowed, but this particular frequency, which is nothing but a center frequency, or this particular band of frequencies will not be allowed. That is the reason it is called notch. That particular notch, that particular band is not allowed, and other than that particular band, all other frequencies are allowed. Not allowed in the sense it is nothing but attenuated. We cannot say completely remove, we can say attenuated. Now, we will see the simulation of how exactly the notch filter works by designing the same filter, right, and output will be taken at this point. Okay. Now, if we see that as similar to that of our previous experiments, how we have done. So, we will go to multisim, we will try to design the same. So, we will take 3 resistors and 3 capacitors. If you remember correct, R1 and R2 should be double than that of our R3 values. So, what I will do is that I will take 3 resistors, the value of this is 6 mega. So, I am replacing the resistance with 6 mega, and other resistor should also be 6 mega, sorry 12 mega, and one resistor should be 6 mega. So, this should be 6 mega resistor, and let me delete this, so easy to create. Then other one should be 6 mega, R3 resistance should be 6 mega. Now, we also require 3 capacitances. So, capacitor 1 C1 I am saying it as, which is nothing but 270 picofarads, 270 pico, then 2 capacitors, and the value of capacitors should be half of that of our C3 capacitor. So, C3 capacitor is somewhere here, right, and the value of this should be double than that of our C1 and C2 capacitor, which is 540 picofarad. So, whatever the required resistors, capacitors, we have arranged it here, and only thing left is connections. So, the passive elements connections we will do now, then we will go with our active elements required. Right. So, which looks similar to that of our circuit if you observe here. Right. Now, the input should be connected at this point. So, what I will do is that I will take AC voltage, connect it here, and other terminal should be connected to the ground. So, we are thinking to take a resistance value, sorry, the voltage source with an amplitude of 1 volt peak value. So, peak to peak we can select it as 2 volts too, right. So, it is easy to understand, relatively it is easy to understand our output voltage. So, and we need 2 op amps. So, 1 op amp we are taking it here, and as the purpose of this op amps are, one is to provide an impedance mismatching, other one is to provide some offset to the system. So, what we do is that we will flip the op amp. So, the op amps look similar to that of our, the connections will look similar to that of our connection that we see in our circuit board, right, and we will take one more op amp, rotate it, okay. So, this one should be connected to the second point, the junction of the C3 capacitor and R3 capacitor, and one part we will take potentiometer. So, the output some percentage is passing through our input. So, this particular terminal has to be connected here, right. So, we made the connections whatever we required. Now, we will test for the functionality. So, as we are following the frequency analysis in order to see how exactly the frequency domain looks like. So, as remember, the notch filter will pass a frequencies from 1 hertz to somewhere around except the narrow band frequencies, it will pass all other frequencies. So, in order to verify, we will go to AC sweep, we will keep some settings here 1 hertz, and the stop frequencies we may not require up to 1 e power 10. So, we will go up to somewhere around 200 hertz, and the decade value we will say points per decade, 10 points per decade, then logarithmic scale, then start simulation. But in order to visualize, we have to put our voltage points to, one green indicates our input voltage and blue represents our output voltage. When we start our simulation and we look into the graph, one thing is clear that if you clearly observe, so it has two different frequencies, input phase as well as magnitude, input output phase as well as magnitude. Since we are not interested in the phase 2, we just look into the magnitude. If you see that the output as well as input, right, output and input are having the maximum amplitude magnitude as 1, right. That means there is no gain acting in the system. Now, what we do is that we will see, we will try to increase the frequencies to somewhere around 1000 hertz, so that even the output can go to the maximum right, the gain. And let me remove the phase values. Now, if we clearly see that this is 10, it is in a frequency domain. So, if you recall how do we measure in a frequency domain. So, and that in a log scale basically 10, 20, 30, 40 and 50, right, 60, 70, 80, 90, 100. Now, when we see that we need to know 3 dB line, this 1, 2, 3, this point, right, this particular frequency, the frequency at this particular amplitude, right, is the cutoff frequency generally we do. But now, if you see at a frequency of somewhere around 50 hertz, right, the magnitude is completely very smaller, right, and again suddenly after just above 50 hertz it started raising. So, when you see the valley, it is just like a narrow, that is why this is called narrow band filter too. So, very narrowly we can sharp down, we can cut down into one particular frequency. The reason is that we are looking to eliminate or to remove only the 50 hertz noise, and other things we are not we do not have to remove it. So, that is the reason rather than going with a long range of notch filtering, if we can go with a narrow band of narrow filtering, narrow band of our narrow filtering, it would be really advantage, so that it can only remove 50 hertz frequency signal. Now, so this looks similar to that of our narrow band frequency. Now, how do we understand, since most of the cases we may not have a function, we may not have the frequency spectrum to visualize our filter. So, what we can do is that we can even analyze the cutoff frequency of the filter by looking into the time domain. That is what we are even visualizing in our previous experiments too. Now, how do we do that? So, rather than going to AC sweep, we will go to interactive and we will try to change the frequencies slowly from 1 hertz to up to 100 hertz is more than enough, and we will put it in a split mode. Okay. Now, if we observe, let me run, right now it is 1 volt 1 hertz. Let me change the settings of our time domain of our signal, right. So, we have both the signals, if you carefully observe, right. The reason why we are showing only one is because one is ahead of other, I mean the green is on the background of the blue color. Okay. We slowly change our signal frequency at an intervals at the steps of 10 hertz. So, now we will go with the 10 hertz. Now, if you observe, let me change our time divisions, right. Here we can clearly see that this is our input green color and this is our output. Now, how do we understand this is the particular point that we have to consider it. So, in order to make ourselves easy, let me create a cursor for us. So, the cursor point should be somewhere around 707 millivolts. So, let me move very close to, if you observe here at this point. So, I just keep the cursor at 707. So, this is nothing but our 3 dB line. What we do is that when our output voltage is lower than this particular 707 or at 707, that is nothing but our cutoff frequency generally we consider in our frequency domain. Now, the output is greater than that particular cursor point. So, that means this is not our cutoff frequency. Let me increase to 20 hertz, we increase almost close to, but not exactly, right. Then 30 hertz, see below that 40, very small signal, 50. So, that means if you observe that there is a drastic change for every 10 hertz increment, right. That is why this is called a narrow band, a very drastic change, right. Now, if I slowly increase the input frequency, even you can observe the drastic change in our output signal too, right. Now, what is the purpose of the op amp that we have seen here? If you observe, so what we do is that to understand that op amp, we will keep to one particular value. Yeah, we will consider this one. Now, we will change this particular resistance. Sorry, this should be 10 kilo, and let me change this value. If we observe, right. Now, how much band, how much narrow band that we require, we can select by using this particular pot. Now, we will slowly change once again. 17, 25, 26, 30, 33, right. At this particular frequency, somewhere around 34, right, somewhere around 33.5. If you observe here, it is very close to our C1. So, what if I increase it? Okay. So, if I see that till that particular frequency 39, now it has increased to 39. So, that means we can see at what frequency that we require to have the proper cutoff, right. Now, if I slowly increase, 44.45, let me see, take 45. Okay. See, there is a drastic change from 44.5 to 45 itself, and since our interest was somewhere around 50 hertz within the range of plus or minus 5 hertz frequency, from 45 hertz to 55 hertz frequency I am completely eliminating. Even if it is not even required, what we can do is that even we can change this R4 resistance to some other value. So, we can see a very drastic change, narrow banding of the frequency, everything. But the problem with this thing is that we can, when we closely look into the grapher, there is some shift. There is some shift in our output signal too. So, to understand, let me zoom little bit, right. So, as long as if we keep on change our the potentiometer value, it causes to create some kind of shift in our output signal. So, if that is okay, that is fine. If not, try to set our op amp the resistor to one particular value and change our resistance values. So, but if we are really interested in a narrow band of frequencies, one good way is changing the resistance value, and we can observe that there was this drastic change from 44 hertz to 45 hertz itself, and below that particular value it will be completely below the set off. And if you see even that, go to split, and if I slowly increase input frequency 45.5, right, at 49 hertz almost nothing. If it is 50, again started increasing. Forget about C2, right. But as the frequency is greater than the value, again it follows the input, right. So, this we can clearly understand whether whatever the filter that we have designed can cut off very close to the 50 hertz frequency or not, right. Now, we will how do we perform an experimental thing. When we look into our board, if you recall, this particular portion we have used for both low pass and high pass filtering, right. So, this portion is for low pass filtering, right, and this portion is for high pass filtering that we have used. Now, the other part that we are using is notch filtering and that too 50 Hz notch filtering. So, if you recall our resistance value that we have used that time, so somewhere around 12 mega and 6 mega resistor, 270 picofarad and 540 picofarad, right. So, since 12 mega getting a 12 mega resistor is really hard in the market, so but we can get 10 mega resistances. So, either you can go with a 10 mega plus 2 mega, so that is a one way, or you can use some other combinations in order to get 10 mega value 12 mega value. So, in this case we have used somewhere around 20 mega and 20 mega connected in parallel, and we have connected it, and 6 mega also. So, we have we adjusted the resistance value such a way that to get the 6 mega resistance, and apart from this everything as per the circuit. So that if you observe at this point, we have a different resistors connected in parallel, right, and connected in series, right, series, parallel, again parallel and series, and the capacitor, right, and both the op amps we are using from TL084. So, TL084 is a quad op amp. So, it has a 4 op amps inside. So, we are using only 2 op amps in this point, and this is another part where we have seen even in the simulation where we are changing the shifting our the phase value or shifting the narrow band and everything here, right. So, now let me implement the circuit so that we will see how exactly it is working. So, input at this point is the junction of both 12 mega and the capacitor. So, when we see that, so this particular point is the input to our system, and the output is the 7th pin. This pin is the output for us. Okay. Now, what I will do is that I will take CRO, I will take function generator, I will connect input from the function generator, right. If you remember, we are going to use a function generator starting from frequency of 1 Hz to a frequency value of 100 Hz. If we slowly increase our frequency, at one particular point we can see 707 decrease in our lesser than 707 or millivolt output voltage. That frequency at that frequency it is nothing but a 3 dB line. So, I am connecting the input here and changing the input frequency to somewhere around 1 Hz, and so I will take CRO. So, one terminal connecting it to the ground, other terminal I will be connecting at the same input point, so that we can see what input that we are connecting it to the system, right. So, I have taken CRO, one CRO probe, connected at the same point, right. Another CRO probe, let me connect it to the output. So, this should be our ground, this is the ground, and this should be our output. The 7th pin is our output. I am connecting it to the output. Right. So, let me switch on the circuit. Let me switch on the input signal to auto set it. So, when we look into the CRO, right. So, this is nothing but our input, the yellow color line, and the blue color line is our output. So, just to understand, what I will do is that I will keep both the signals to the same point at this particular point, so that it is easy for us to compare. Okay. Now 5 volts. So, let me change my amplitude to 1 volt. So, I am setting the amplitude to 2 volts peak to peak. So, that is nothing but 1 volt to peak. Now, I will zoom this particular. So, if you see, one box in this case represents 5 volts, right. Even in this case one box represents 5 volts. So, let me increase the value, one box to 1 volt, and even here. Okay. So, there is slightly shift of our output. So, that we can adjust by changing the pot, right. So, let me change the pot value. When we look into CRO, we can see we are getting both input and output signal. Now, what we have to do? We have to see whether this particular circuit is filtering out the 50 Hz component and other frequencies are passing or not. So, for that we have to change our input frequency, and we have to see at what particular frequency the output is below 707 millivolt. So, in order to set 707 millivolt, I will use a cursor. So, I will go with a cursor and I will make it as an amplitude cursor for channel 2. So, I will go for channel 2 and sorry. Okay. So, I will change the cursor 1 value to where is it? So, the peak value when I take, so this is the value, and another channel I am moving it somewhere below. So, the peak to peak value when I see delta V, it is 2 volts, that is cool. Now, so this is our ground terminal and this is 720 milli. So, right, channel cursor 1 is the difference between both the cursor 1 and cursor 2 is somewhere around 720 millivolts. So, now what I will do is that when we look into the function generator, I will slowly change at a frequency of 20 Hz. So, now it is at 1 Hz frequency, I will change it to 20. Okay. So, to 10 first, to 10 Hz. Now, when we see, right. So, I do not see any difference in below that particular value. So, let me change to 20 Hz, even the result at the same, 30, even higher than that of the cursor value, 40, slightly higher than that. From here I will slowly increase 41, 42, 3, 4, 5, right, 6, 7, 8, 48, 49, right. When we observe that somewhere near to 49, somewhere near to 50 hertz. So, when we see the CRO value 50 hertz, that is the output is almost below the cursor value, right. When I slowly increase here and there, the amplitude will be, the peak to peak amplitude we can see it is completely decreasing it, right. And if it is increasing, again the peak to peak amplitude, if you observe, starts increasing. Now, okay. So, in order to make it narrow band or something, what we have to do, we also have to change the resistance value. So, I slightly change the resistance value to because we need narrow band. So, that is the reason by adjusting your resistance value, we can easily see whether it is creating a narrow or little wider band, right. So, that is the reason I change the resistance value. I am decreasing somewhere to 53, 52 hertz, 50 hertz and 49 if it is higher. So, there was no much in fact now. So, if you recall our the pot resistance value that we have chosen. So, if that same resistance value, if I measure and select it, right, we can see. So, I am adjusting the resistor. So, we can see it has come down. Right. Whereas, if I change the resistance value, the pot, the peak to peak voltage value will change it. You can easily see the CRO, right. So, depends upon whether we require narrow or wide band. So, this pot, the pot that we are using decides it, right. So, this way we can even change the notch filtering to be narrow band or little wider band and everything.